Hi.
Hello and welcome to Calculus 3.
Do you always set your courses off like that?
Yes.
Oh.
Every time.
He has a script.
So, at the beginning of Calculus 3, we have to talk about vectors. Calculus 3 is going to be mainly in 3D, but we are going to have some 2D stuff and some 4D stuff. We are going to see that as we move along. But first we have to talk about vectors. We're going to talk about vectors in 2D in the first lecture, 11.1, and then vectors in 3D, 11.2. But vectors can sit in any dimension. Vectors are just our mathematical constructs. Vectors do not exist. Like numbers. Numbers do not exist. Right, you don't see number 3 walking down the street. But we understand the concept of a number as the abstract idea, and we understand what the meaning of having the 3 people or the 3 cats and 3 p.m. and so on. So we understand the concept of the number even though it doesn't exist in the physical realm. So vectors are pretty much the same idea. It's a mathematical construct that we use extensively in physics and engineering, but it actually doesn't exist. We use it to explain other concepts, to understand other concepts, and to calculate, right? So vector is going to be this mathematical construct which has magnitude and direction. So vectors in space have magnitude and direction. Now note that I use the word space. Now space could be one-dimensional space, which is just a number line where you have numbers from negative infinity to positive infinity, and that would be one-dimensional space. And then you have the two-dimensional space, which is XY space. You are familiar with that one. Pretty much all of your mathematics so far has been done in that space. And then a 3D space, XYZ. 4D space, XYZ, you can use T as a time or W as the fourth dimension. So the number of variables you use is the dimension of the space that you are in. So when someone is talking about n-dimensional space, it just in mathematics simplifies down to how many variables do you actually have in that space. You are familiar with y equals f of x, and since you have x comma y as the ordered pair from that space, it's a 2D space. So two-dimensional space because there is dimension x and dimension y. It's very simple. We are going to cover functions z equals f of xy, which creates xyz as a point, which is a 3D space. And you can go to as high as you want, which is why the linear algebra is so important. Generally, Calculus 1 and 2 are two-dimensional. Calculus 3, 3D, peeks into 4D a little bit. But if you want to generalize certain things to any dimension, yes, you will go and you will take linear algebra and understand the higher dimension. That course crowns over all of calculus and everything else that you studied so far. So now, when we understand the space, that space has dimensions, we are going to look at this room and realize that the floor, right, is going to represent our XY 2D plane. And you can pick one of the corners in the classroom to be 0, 0 on the floor, and then have a positive x-axis along one of the walls and the y along the other wall. And you can map a location. Actually, we have a much better grid on the ceiling. It's already, the grid is already there. So you might be sitting under one of the intersections, and you can just count the amount of tiles, and your position might be 7, 3, or something. Yes. So we can put this grid, right, the 2D grid. And then you have the box, which is the box we're sitting in, the classroom, right? And that's a 3D space because we have a 2D floor, and then we have a third dimension, which is the walls going up, and we can locate every point in space with a two-dimensional location on the floor plus the height above, which would give us the third dimension. So now, vectors will be stretching between 2 points. So we first talk about the two-dimensional space, so vectors in 2D. Vectors in 2D. So we are going to take a look at a vector which stretches between point P and the point Q. And we'll say vector lowercase u with the arrow above it. So vector u can also be written as vector PQ, P being the initial point, and Q being the terminal point. Now, in 2D, initial point P will, let's say, have x, p, y, p coordinates, and x, q, y, q coordinates. So now I can find the vector u, which is the vector pq, by simply subtracting. Now, there's a lot of notation here that I'm introducing in one shot, but deal with it, right? It's xq minus xp, comma, yq minus yp. Know that these are spiky brackets, and the spiky brackets means vectors, all right? You have parentheses. So now, notation. Here, I'll do that in red. Notation. This is not red. It's whatever color this is. Notation. So, vector u, we know it's a vector because of the arrow. PQ, again, vector because of the arrow. And spiky brackets xy, I know it's a vector because of the spiky brackets. This is a point. It could be open interval as well. Point or open interval. Now, it can't be open interval because xy. It's x1, x2 is the interval. Okay, so point in 2D because parentheses. So, you have to be careful. Oh, wait. Okay, so I see the issue.
Just smack it. Like hard.
It's tall enough.
It's like
That's we're going to cover that with vectors.
like 5 newtons.
So should we move the projector or should we move the screen?
Projector. I think the projector.
I have no clue. Can it? That works. Good.
That's the we do.
So this is all the notation. Now, you have to be very careful with the notation because you have to put these vectors. In the textbook, they put bold letters. So when they put the bold U, they mean the vector, right? It's a little difficult to do that in your notes. So you need to use the arrows in the notation. In a textbook, they generally use the bold letters for vectors and regular, right, for points and so on. So that's the notation. So now if I have to the system xy, I have a point over here. This point is -2, 1. And I have another point over here. This point is 1, 2, 3, 4, 3. I can stretch a vector between these 2 points, and this vector u will be given as the vector of 4 minus -2, comma 3 minus 1. So vector u is given as 6, 2. So vector is 6, 2. Now, observe this. The length of this red line is actually 6. And the height of this red line is 2. It's exactly what we got from this calculation. All right? So it's terminal coordinates minus the initial coordinates to give you the vector. Now, the vector has the magnitude, and the magnitude is the length of the vector. Now, if you use the vector to say to describe a force, then the magnitude of the vector tells us the size or the magnitude of the force. Means the difference between, right? So that's the difference with what the magnitude gives us. In terms of velocity or speed, right? Velocity, right? 30 miles per hour versus 60 or 65 miles per hour. So the magnitude will show that. And the formula for magnitude, well, first off, the magnitude is given as the magnitude of vector u. Those are the absolute values around vector u. And it's given simply by the Pythagorean theorem, the x coordinate squared plus the y coordinate squared of the, right, because we have 6 and 2. So in our case, right, for our vector would simply be 6 squared plus 2 squared, which is clearly 2 root 10, right? So we have the magnitude for our vector to be 2 square root of 10 by calculating these concepts. So that's the magnitude, and then we have direction. Direction is the angle with positive x-axis. And we generally use theta for that. And if you are to look at the picture above, right, theta is going to be inverse tangent of y divided by x. So in our case, inverse tangent of y, which is 2, divided by x, which is 6. So inverse tangent of 1/3. Now you can use the calculator and get that in degrees or radians, depending on what you guys want to get. So the vector doesn't exist. Vector is mathematical construct. We can use the vector to describe either things or concepts. For instance, right, if you look at me right now, I can be replaced by a vector that is 6, 1 in terms of the length, because that's my magnitude, and my orientation to the x-plane is going to be 90 degrees, or pi over 2, right? At some point later, tonight, this particular vector is going to be horizontal, right? It's going to still have the magnitude of 6, 1, but the direction of the vector will change, right? It will be at 0 degrees rather than at 90 degrees. So we can use it for objects, right? But we can also use it, as I said, for the force or the speed or some other concepts in physics and engineering that arise. Now, very important to understand that vectors are free to move in space. And that two vectors are the same if their magnitude and direction are the same. So now these two together work, with the idea that you can move the vector and it's still the same vector. So if I have a vector that it's 45 degrees starting at y equals 1, then this vector is the same. So if this is vector u and a vector v, in this case u is the same as v. And we can just say, you know what, just move the vector u down 1 unit and it becomes vector v. These two vectors are the same. We don't care about their location in the system. What we care is that they have the same direction, which is 45 degrees in this case, pi over 4, and that they have the magnitude of what is this, 2 square root of 2? So that's all we care about. And that will be useful later on. Now, you can also think of vectors as multidimensional numbers. You see, in the 1D space, on the number line, which is 1D space, I still have vectors. And if I keep 0 as the point of origin of every vector, I can have positive and negative numbers explained very well using the vectors. So what is number 4? Number 4 is going to be a vector which stretches from 0 to 4. Now, what is the magnitude of that vector? Magnitude of this vector, let's call it vector u, is going to be 4, because that's its length. What is the direction, theta? Well, it's 0 degrees, right? On the other side, I can have, let's say, vector v to go to negative 3. What is the magnitude of vector v? It's 3, because its length is 3. And then the theta direction is going to be 180 degrees, or pi radians. So you see that I can represent all of the numbers. If you're having issues seeing that, there you go. So I can represent the one-dimensional, the numbers, right, on one-dimensional line. I can represent that with vectors easily. Now, you can think of two-dimensional vectors as two-dimensional numbers that have a number that goes in x direction and a number that goes in the y direction. And it's easier to us to think about those two-dimensional numbers in terms of magnitude and direction, rather than worrying about two separate directions in which they go. So we introduce a vector in the xy plane, and we have the magnitude u, and we have the direction theta for each one of these vectors. Now, the notation, as I mentioned before, so if this point over here is xy, note that I'm using parentheses because it's a point. I can also say that the vector u is xy with the spiky brackets. All right? The magnitude of u is going to be given with the Pythagorean theorem, and the direction with the inverse tangent of y over x. So as soon as I give you the values for x and y, you are able to do this. But now there is another notation that I want to introduce, and that is ij notation. I'm going to write x I plus y j. Now these guys should have a little hats on them rather than arrows, even though these are vectors. But they're special kind of vectors, unit vectors. We'll talk about unit vectors as well, right? So this is just another notation, and I'll talk about these. So I'll just write now I and j are unit vectors. And I will come back to that point. I just want to introduce that notation as well. All right, so now if you are regarding vectors as numbers, what can you do when you have two numbers? You can add them. Very good. That means that you should be able to add vectors. Now that makes sense, because if you represent a force with a vector, right? Let's say, I don't know if you've seen those videos when you know, the Tesla car is pulling an airplane or pulling a semi-truck, or, you know, right? So how about you use two of those cars, right, to pull, right? You can. Can they pull more together? Yeah, they can, right? So if you think about the force, right, the pull, right? That's why, you know, you have two people lift certain things rather than one person lift, right? You get the piece of furniture, and you have two people to lift rather than one person to lift. So when you are thinking about the vectors in terms of numbers, well, yeah, you can have two vectors and then they add. Now, direction is important because, I mean, say you want to move a fridge, right? And then you have, this is a fridge, right, on the floor.
And the Tesla's pulling it.
No, Tesla, you're pushing.
Okay.
Right?
I got it easy.
So you are pushing this. It's clearly you because I have a cat. It's more like this.
Yes.
There we go. Well, actually, now that I look at you. So now, right? But then, clearly, you will be pushing this way because you want the fridge to go this way. But then you have your troll friend on this side, right? Oh, do you have friends?
No.
Oh, okay. Then, well, I said a troll friend, but then you could. So I had to ask. So now this one is pushing this way, right? And it's clearly going to be whoever is stronger, the fridge is going to go that way, but it's not going to go with the force of the stronger one. It's going to go with the difference of the two force, right? So the idea is to add the vectors, right? You will add x component to x component and y component to y component. The resultant vector is going to point in the direction of the stronger. Now, if both are pulling the same way, right, then yeah, it adds up. So you can think of a big, let's say, a tanker ship, right, which has, I don't know, it's a huge ship with a lot of crates and stuff on it, right? Just leave me alone. Whatever. And then you have two small tugboats pulling right this way. So the vector going this way, vector u, and a vector v, right? They will clearly add u plus v, and the direction of the force experienced by the tanker or the cargo ship or whatever. Yeah, why is it called cargo? It's on a ship. It should be shipgo. Yeah. So well, this is on the water, so don't worry about it. So the force of pull would be both of these small tugboats together, right?
Minus the current.
And this is like friction.
That's true.
You would call it friction.
I give up. Between the water and the ship, yes, there is some. Completely negligible. Now, there's also friction over here, right?
Well, the force of the waves,
It's
maybe.
not
Could
completely
be a rough day on
negligible
the
if
water.
it's submerged to a certain degree, because then
Yeah.
you're moving
What
the
if it's
force of
something
the water in
we're
front
gonna
of
hold to the
it.
side?
You're sinking, so it's louder.
Exactly. Thank you. Thank you. You're singing. So
Is she getting offended?
I'm
Oh.
not offended.
No,
Yeah, I think
you're not.
No, she just wanted to end. Yeah.
I just want to
We only have another hour and a half, so make it count, right?
What?
30 minutes.
No, whoever wants to leave.
Yeah.
You're free. All right, so so now vectors add. So if I have a vector u with x1, y1 coordinates, and the vector v with x2, y2, the sum of these vectors u plus v is going to be simply x1 plus x2, comma, y1 plus y2. And that would be sum of the vectors. So to add vectors. Now, subtraction of vectors is actually the same thing. You just go component-wise. Now, observe the direction, right? In a situation with pushing the fridge, right? Two guys are pushing in two opposite directions, so their forces, their vectors will actually subtract in that case, and whoever is stronger, the fridge will go that way. Where in the case of the boat on the right, it's definitely going to push to the right with the combined force of both of these tugboats pulling together.
Cargo should have like a rudder though, going in opposite direction.
Yeah.
Why?
No, that's an example of an opposing
It's
force.
something where cargo ship can only go forward, so that means you'd have to turn the whole vessel around.
I don't know that. I'm just saying it could be in reverse.
Yeah.
Yeah, exactly.
So now,
Oh, this class is
I'm trying to make the summer fun.
like math isn't fun enough.
No.
noted.
No. Physics is the fun part, actually. Math is the tool, right?
Physics is
What's
just
that?
applied math.
Just. And then engineering is applied physics, and then, right, so we can go in
It's
layers.
just apply math.
Yeah, I still sit on the tops. Yeah, good. Right. So now, graphically, to add vectors, you will go what we call head-to-tail method. where you say have vector u and vector v. Remember that vectors are free to move in space, which means that the vector u in this case will go here, and that will create a resultant vector of u plus v, or vector u, which is the one that I moved up because they're free to move in space. Again, you can consider my pen that I'm writing with as a vector, right?
Yeah.
And it has its magnitude, which is how long it is. Right? It would be kind of hard to wield this if it was the same thickness, but let's say 5 feet long. It will be harder to manipulate with it. So, those are the things that are actually considered in the design of these things, right? And now the direction in which I use this pen is important, because if I use it tip down, it writes. If I use it the eraser down, it erases, right? So that is your theta, right? The angle at which, right? And then you can have it completely useless if you just rest it next to it and it doesn't do anything when you move it. So direction matters. So we can link. Now, what I was talking about is having a pen, right? And when you use it the right way, it works. If you use it the opposite way, it doesn't work, right? But now, since this is the length, I can link two of them and still have it, right, work. Now, it doubled the magnitude, so it really didn't do anything for writing, but it made the object at least bigger so I can find it easier. Like, let's say that's a plus. So you can have the microfiber cloth. Called it a rag, almost got killed by the VP. So microfiber cloth. So vectors can be added together. A vector can be scaled. You can multiply a vector by a number, that it's either a fraction or a whole number, and that will make the vector shorter or longer, depending with what you multiply it by. So if I have a vector in space, let's say that's vector u. If I put another one over there, then clearly u plus u is 2u. So that is going to be a scaling factor. So I can scale vectors. What is this now? Can anyone explain to me why is the thing beeping? They kill far more people going forward than backwards. It should be beeping going forward.
I think they cause more accidents going backwards.
Nah.
It is a little harder to see behind you when you're like trying than going forward,
Yeah, what was the part of natural selection earlier? Can we have a little bit of that?
Just a quick question.
Yes.
When you're adding, you can add the vectors together. When you're adding like just a number to it, is that just moving it around?
When you multiply it by a number, you would stretch it or shrink it. When you add two different vectors, you are changing their direction and their magnitude. You don't get to move it that way. You add numbers around and you move functions, not vectors. All right, vectors are free to move in space anyway. So the vector is perfectly defined no matter where it sits in the coordinate system. So if I have a coordinate system and I have a vector over here, this vector u is given as 3, 1 no matter where it sits. So I don't need to add or subtract any numbers from it to shift it around, because I just pick it up and move it here and it's the same vector, right? Except when it's on its original position, starting at 0, 0, it will reach 0.31. Where here, you are at 3, 2, going into 6, 3, and then you have to do some math to figure out what the, right? You have to do the subtraction to figure out what the vector is. All right, so that's that for the basics of vectors and things. We know about the magnitude, we know about the direction, we know how to add and subtract vectors and multiply by a constant. Maybe I should add over here again in red that constant times vector u will just propagate into cx, cy inside the notation right there. So now we can think about working with vectors in the sense where I say let vector u be 2, -8, and vector v, let's say, is -3 and 1, whatever. Compute 3u minus v. So try this one. All right, that's enough time. I'm going to write this as 3 times 2, -8, minus -3, 1 vector, which is vector 6, -24, minus -3, 1. Combine x components together, we have 9, and then combine y components together for -25. So the whole new vector that we get should be 9, -25. Cool? Everyone okay with this? Good. Now we're going back to our talk about those I and j vectors that I mentioned briefly earlier. I can write this as 9i minus 25j, and I told you you put these little hats on top. So the hat notation, which is this little hat on the vector, denotes unit vector. What is the unit vector? Unit vector has magnitude equal to 1. We are going to have a lot of these unit vectors around. There will be a unit tangent vector. There will be a normal unit, a principal unit normal vector, and so on. The unit vectors are going to play a huge role in chapters 11 and 12. You absolutely must know unit vector. How to find the unit vector? Well, the unit vector is equal to, you take your vector let me first do the notation. So you take the vector u and you divide it by its magnitude, or if you want your xy notation, you take xy and you divide it by its magnitude, x squared plus y squared. This is your unit vector calculation. The first two unit vectors that you learn are principal unit vectors for 2D space. And those two coordinate unit vectors are I with a hat, which is given as 1, 0, and j with a hat, which is 0, 1. So these guys are actually the coordinate unit vectors because they help us break our vectors into components. So let's take a look at, 3, 4 vector is actually 3i plus 4j. The meaning of this is in the coordinate system xy, I'm going to lay down 3i vectors, and then I'm going to have 4 j vectors stacked, and as you can see, we are getting our vector u, which is 3, 4. It's a very simple concept. What are these guys? These are actually your number 1 from your one-dimensional number line, right? You have number 1, 2, 3, 4, 5, and everything is in units of 1, because 1 plus 1 is 2, and then plus another 1 is 3, plus another 1 is 4. So 1 is the unit, right? So now you have 1 as a unit for x, but you also have a 1 as a unit for y. And that's why you have 2 separate ones, because it's a 2-dimensional space. So whatever is the role of number 1 on the 1-dimensional line to create, right, the number line from negative infinity to positive infinity going by increments of 1, that's what I and j do for a 2-dimensional space. I, j, k will do the same thing for 3D. Now, clearly, vector I has a direction of 0 degrees, and vector j has a direction of 90 degrees, or pi over 2 radians. But the formula over here, in red, indicates that we can have a unit vector in any direction we want, because any vector can be turned in the unit vector. So what I can do is I can take this vector 3, 4, and turn it into a unit vector. And I do that by taking 3, 4 and divide it by the magnitude of 3, 4. So what is the unit vector u? Look at the notation. Notation changed. It has a hat now. So 3/5 and 4/5. Right? Because 3 squared is 9 plus 16, 25, square root of 25 is 5. So, guys, we have the vector u with the arrow is a vector whose magnitude is 5. U hat is the unit vector whose magnitude is 1. Go ahead. Check that the magnitude of this is 1. You know the formula. Square the first fraction, square the second fraction, add them together, take the square root. You have to get 1. Because unit vector is defined as magnitude is 1. I actually never checked if the stream is going. Yeah, it's live. So, to check, I will go 3/5 squared plus 4/5 squared is 9/25 plus 16/25, which is square root of 25/25, which is 1. And that's the magnitude, right? So vector u hat is the unit vector because it has magnitude of 1. And that's the unit vector talk. Now we are going to use unit vector a lot. As I said, unit tangent vector, principal unit normal vector. We are going to have directional derivatives eventually in chapter 12. Again, unit vector will play the role there. So you need to make sure that you know and understand how to deal with the unit vector. At the end of the lecture, we have properties of the vectors. Now, these properties are actually for any dimension, not just 2D. And after that, some word problems, and we're done. The reason why I say any dimension right now is purely because I am lazy to write this list again for our lecture tomorrow. Our lecture tomorrow, 11.2, is going to be on vectors in 3D. And they are going to have the same properties. So let's see what the properties are. There are 10 of these properties. Number one is that vector addition is commutative. So u plus v is the same as v plus u. Right, so commutative rule. Then we have associative rule, where you are adding 3 vectors. So it doesn't matter which order you add these. If we add 0 to the vector, you add, a 0 vector to vector, you get your original vector back. Now, 0 vector is vector of all zeros in there. So if you are on 2D space, it's 2 zeros, which is the origin. So that's a 0 vector. 4, if you add vector to its opposite, you get 0 vector on the other end. Rule 5 is distributive property for constants, and it goes 2 ways. If you distribute C into sum of 2 vectors, you get this distributive property. By the way, just as a reference, something like this would go on your class prep. So everything that I wrote in red and like definitions and things, those are the things that go on a class prep. And if you want, you add pictures, examples, and things if you need them.
So anything colored?
Well, you're doing class prep before I lecture, so yeah. We can also distribute constants. Vector to constants. If you multiply 0 times vector v, you will get a 0 vector. Let me write this in blood. 0 is not the same as the 0 vector. So make sure you know that.
D is some other constant?
D is just another constant, yes. Scalar, right? Constant times the 0 vector is the 0 vector. Number 9, 1 times vector v gives you back vector v. And number 10, multiplicative property over here. is that you can multiply constants first and then multiply that into vector v. So these are the 10 properties. And we have these side notes. Maybe I should change this into red as well. So 0 vector is the vector of zeros. For 3D 0 vector, you will have 3 zeros, and 4D you will have 4 zeros, and so on.
So like we have to memorize those, or it's just properties?
These are the properties that you might use here and there for calculations. Now, technically, if you look at the one-dimensional case, you get your basic algebra properties. Basic algebra property will say, well, arithmetic property, a plus b is the same as b plus a. It's commutative, right? Now we did the same thing for. So technically, you already know all of these things intuitively. What's 0 times 3? Well, it's 0, right? Well, now you do the same thing for the vector. Over here, 3 times 0 is 0, right? So these are the things that, pop up. This one you can understand as 2 times 3 times x is the same as 2 times 3 times x, which is 6x. And you know that when you multiply 2 times 3, right? So this is just the algebra recasted into the vector realm. So these properties should make sense if you find their counters in your one-dimensional world that you already know from algebra and arithmetic. And finally, we have the application and the use of vectors. Physics and engineering, obviously, the leading fields that will use this concept and this idea. The good thing about physics is the fact that physics is arrogant in a sense that, we only care about the center of mass, and the rest of the object you can just throw away. So let's say, okay, let's think about, I don't know, an elephant. And they say, great, in physics. They say, okay, the elephant is here. And then we have to do something with the elephant. Like, why is the elephant a dot already? Because the elephant, why did I pick elephant? Can I draw the elephant?
Fish, do fish.
You can do it.
I love it. Actually,
Got a mustache?
it's the tusk.
It's the tusk.
You're doing well.
You're really focusing on tusk.
Well, there is the ear that goes like this. And the eye. And the tusk should be bigger.
Where's his mouth?
All right, the mouth is right. No, mask is behind the tusk. But
Now it looks like
Now.
I put a fang on it, so it's really weird.
it's a deep.
And it has the big feet. It should be fat, but it's not. And I don't know.
Get the muscle definition in there.
Yeah, I know. All right, fine. There's the elephant. Right. What is important is that the elephant is going to have a center of mass somewhere, right? So with the center of mass on this elephant, you can just forget about the elephant, and there you go. The whole elephant is right here, right? That's the elephant. So the center of mass for the elephant. Now, you know what this elephant is going to? It's going to be heavy, right? So you're going to have a force of the weight for this elephant. There's going to be that. And there will be a normal force on that elephant, because when the elephant sits on the ground and pushes the ground pushes back. So that's the normal force, right? And when they equal each other, the elephant is in equilibrium. The elephant is not going into the ground, or, right, the ground is not going into the elephant. The same concept, guys. You're sitting on these chairs. Your weight is pushing down the chair. The chair is pushing with the same equal, well, except you now, because you were rocking, but everyone else. And the idea is, right, to have a stable system, these vectors are going to equal each other in the opposite sense. Now, the stuff changes where you have a crate or the elephant on the incline, and let's say sliding down the incline. So let's put the crate on the incline. What happened?
Pretty decent triangle.
That's what I do. Everything I do is decent. But you're not used to it yet.
Great, just decent.
The crate
Just
is
passable.
pretty good too.
Yeah,
No, I think it's pretty darn good. I can't get it.
practice. So what do I have on this crate? Guys, we're going to have a normal force, which is going to be perpendicular to the surface. We are going to have the weight, which is always pulling directly down. We are going to have a friction force. The friction force is going to oppose the motion, which is down the incline. So when you are looking at this system, right, you see that the incline angle at, let's say, 30 degrees is going to impact 3 of the forces to be at the angle, and then only the force W is going to. Now, this is way too much for us to draw, right? So what do? In physics, we do the easy thing, right? You say, okay, I have this. This is my normal force. This is my force down the incline. This is my friction pulling back. And then this is the W. Yeah. And now, as you can see, I have to deal with 3 forces that have the 30-degree, so sines and cosines involved. What's better is to rotate the system. So if you rotate the system, then 3 forces become like this. You have F, friction, normal force, and then the weight gets to be the only force where you have to deal with trig. Now, linear algebra teaches you how to transform these spaces to get these things solved much quicker. Now, what kind of concept helps us calculate these things? Well, it's going to be the concept of sum of all forces for the object that is in equilibrium needs to equal to 0. So sum of all forces in x direction needs to be 0, and sum of all forces in y direction needs to be equal to 0. And technically, this with some moments, we pretty much covered the whole class called engineering statics. Right? If you, yeah, that's it. I have one more formula to write, and that's the whole course. Some of you are looking at this like, no, it's not. And I'm saying, yes, it is. It's just, there are subtleties and details, but that's it for the whole course. So now what I want to do here is I want to understand that my normal force, right, is going to be some coefficient of friction times the, coefficient of, coefficient of friction, mu, yes, times the friction F. And then we have force down the incline. So I see that my forces, right, for the x component, I can say I have negative f plus lowercase f plus the component which will be actually minus wx equal to 0, right? And then for these guys over here, for y, I have the normal force that is pushing upwards. And then that needs to be, and then I'm subtracting the wy, which is the, we'll have a sine and cosine of there. And there are 2 equations, right? Some stuff was going to be given to you, so you can practice that. Now, physics actually teaches us a lot of things, and if you study physics closely, you understand. First off, if you are pushing or pulling something, while pushing, let's say, so here's a crate. We have the crate on the on x-axis. Let's say you are taller than the crate. I'm still going to use your hat, right? and you are pushing this thing. Observe that there is the angle at which you are attacking this crate. If you are attacking the crate at angle like this, note that it decomposes to the push down and push forward. So if this is the force with which you are pushing, there is a force Y and the force X. Force X is the only force that does work. Force X does all of the work. What is the force Y, component Y, doing? Yeah, it's making everything harder. See, that's the problem. When people don't understand, right? You want to push something and you push this way.
You're increasing friction.
Yes, you're increasing friction. You're increasing friction because you are pushing it down. You can't bury it into the ground, but you are adding extra weight because this component here was adding extra weight, which with the normal force creates more friction, which makes it harder because friction opposes your motion. All right? So what's the right way to push things?
Straight.
Your arms, yes, straight, right? You are pushing straight. So that means...
So it's a small crick and a smaller person.
Exactly, so that means you don't get to push this.
No, I don't.
Because,
Small to me.
exactly, right? You get to push the fridge, which
Yes.
make sure you give the number and stuff to move something heavy, right? Which is tall at the same time, right? So these are important things to understand, and we can understand them through vectors. So I hope this argument made sense, right? The way these things work. Next class, we're going to do all of this in 3D, and then do some dot product after that. So class preps, next class, 11, 1, 2, and 3 for tomorrow. See you all tomorrow, same room and same time. For those of you that were late, same time. Not same time, earlier time for you.
But time's not linear.
Stop.